rockets do fundamentally comes down to one basic law of physics. You may have heard of it before. It goes like this. It says that for every action, there is an equal and opposite reaction. Now, you may have heard that before. If you haven't heard it before, or if you've heard of it before, you're not entirely sure what it means, it's really straightforward. And I'm going to explain how you kind of already know it. This thing here, I'm going to take this. This is called a balloon. Cool, we're on board with that. I'm going to take this, I'm going to put a little bit of air inside it. Alright, so we got a balloon with a little bit of air. Now I'm holding on to the end of it. If I let go of the ends, what direction is the air going to go? Right? The air is going to go out of the balloon, it's going to go that way, right? What direction is the balloon going to go? The other way, right? I might turn back the other way. You catch that? Thank you. Alright, so we have a balloon with some air in it. The action in this case is the air leaving the balloon out of the opening, but the air pushes back against the balloon. It goes in the opposite direction and it has the same amount of force behind it as the air going that way. So another way that we can explain that has a lot to do with the fact that in any kind of physics, anytime you're dealing with energy, energy is always conserved. You never create or destroy energy. Right, so if I have this little bouncy ball and I drop it at arm's length, gravity's going to pull it down towards the earth. And what's going to happen when it hits the floor? Right, it comes back. Right? Because when the ball hits the ground, that energy is conserved. It still keeps moving. But when the ball hits the ground hits it back with an equal and opposite amount of force. Right? Even though gravity's pulling down, the ball changes direction and goes back up. And that energy is always conserved. Now, if I take another ball like this one and I let it bounce, that one doesn't bounce that well, right? So, in that case, it seems like the energy's disappearing, right? The ball stops moving compared to the other one. But it's not that energy's not being conserved, it's just being changed in a different form. So you can hear that this ball has a much louder thud when it hits the ground. It makes a lot more noise, right? That sound is the kind of energy that's being given off in that case. So, energy is always conserved, and a rocket is just a way to direct that energy in one direction to push the rocket in an equal and opposite direction. Now, I've got over here, it's a real simple demonstration of what we're going to do to make that air move in our rocket. Now, a rocket generally does the same thing as our balloon. Instead of having a big inflated thing squeeze that air out, we cause the gas inside of there to expand by getting it really hot. We light a fire under that rocket, and that fire creates a lot of hot air. That gas expands and takes up a lot of space. So to do a little demonstration of that, I got this. I have something that's actually very cold. This is liquid nitrogen. This is extremely cold stuff. It's about 300 degrees below zero. And I'm going to put just a little bit of it in this little lab flask. Now you can see the thing that happens to it, and I have it exposed to the outside air, is it starts to boil. See all those little bubbles in there? You see steam coming out of there? Now as it's warming up, that gas is expanding. You heat up a gas, it will take up more room. That's exactly what's going on here. This stuff is reaching up towards room temperature. Which means if I put a stopper on top of here, and I cover up that opening, that gas is going to take up so much space that it has a lot of force behind it. It can pop that lid up into the air. Let's see if we can get it to go a little bit higher. Here, tell you what. You guys want to see how high we can get this to go? There's a precursor. We're going to be launching rockets. I'm going to go for height, right? Here, let's get that on there. Give it a good squeeze. And then right? There we go. Did I lose it? Oh, there it is. Thank you. All right. Now, like I said though, with rockets, we have to, rather than start with something really cold, we want to take some air, we want to take some gas, and we want to heat it up in our rocket. A rocket engine is designed to create a lot of heat, creates a lot of expanding gas, which can push down so you have an equal and opposite reaction to launch the rocket up. Now, in order to burn something, every fire fundamentally is made of the same three ingredients. Right? You need some fuel, we need rocket fuel. We need something to light it, a little igniter at the bottom of our rocket. But we also need oxygen, which is extremely important for a rocket because when a rocket launches, it needs to be really efficient. Now, there's a problem with rockets. That is, the heavier your rocket is, the more fuel you need to launch it. But if you add more fuel to your rocket, you're putting more weight on it. So the more fuel you have, the more fuel you need. That means that in order to make a rocket work, it needs to be really efficient. Your fuel needs to burn really quickly and get the most energy you can out of it. So to do that, we take a really powerful fuel and we add a lot of oxygen to it. How much oxygen a fire has a lot to do with exactly how intensely it's going to burn. So air is not the same thing as oxygen, right? Air around us has oxygen in it, but if you just had a big tank of compressed air in our rocket, it's not going to be efficient enough. Because most of the air you're breathing is actually nitrogen, the same stuff that I've been using here. And if I pour it on the floor, it may get a little bit of that kind of gas. But this stuff is not very good for fire. Right? If you have just nitrogen and I take a lighter nearby it, right? That stuff can put it out if you have enough of it. Alright, you can see it has a real hard time. So to make our rocket really efficient, we need a lot of oxygen. And what I'm doing over here is I'm doing the same thing that we use to power our rockets with lots of oxygen. I am making liquid oxygen. Just like we have liquid nitrogen here, I can use that same stuff to turn oxygen into a liquid. Now, in this can, I have this aluminum can sitting up here, and it is collecting oxygen from the air. The way it does that is, you sit outside on a real hot, humid day, you have like a cold drink to keep yourself cool, you let it sit out there. What happens to the outside of that can? Hey, it sweats, it gets that condensation on it, right? That's water vapor in the air, hitting that cold can and turning back into a liquid. It's condensing on the outside of that. What I'm doing here is I'm condensing oxygen on the outside of this can with really cold liquid nitrogen inside of it to get it down to below the boiling point of oxygen. So it's dripping down into this test tube where we are collecting a good amount of liquid oxygen. I've had this going for a little bit. You can see we've got a little bit of liquid in there. And this is a slow process. But oxygen, especially liquid oxygen, is really great for making a fire burn a lot more efficiently. So this is the exact same thing. You ever see a rocket on the launch pad? A lot of times you'll see it will have like frost and stuff collect on the outside of it. That's because a lot of that rocket has stuff like liquid oxygen in it. Now if I take a flame like this little wooden splint, it'll burn up in outside air on its own. If I drop it into liquid oxygen, it makes a lot more fire. Burns up a lot hotter and a lot brighter than you normally would get. So oxygen is really great for making that fire burn a lot more efficiently. We use this exact same stuff to launch rockets in the real world. But I think now that we kind of explained all these other principles, I think it's time that we should go ahead. Let's launch a rocket for real. You guys ready? We're going to launch our rocket. This is our rocket track down here. So we're going to launch, we got a controlled environment, we're going to launch a rocket from one side to the other here. Now, you guys over here, you guys are kind of in the path of our launch pad. So I'm going to ask you guys to go ahead and step down to the bottom of the ramp.